Okay, so we've got a handful of things to do today, mostly dealing with continuity and differentiability. In order to be continuous, we have to have both a general limit and plug in to get the same point. If I am removable, then we've got a general limit, but when I plug in the point, we're somewhere else. That could be one of these two options. If I'm non-removable, we've got several different types of non-removable discontinuities. Infinite jump essential, also oscillating that I'm not showing here. If we are differentiable, then we have to be approaching the same slope from both sides, as well as have a general limit and be at the same point when we plug it in. So we have to be both continuous and approaching the same slope. I think we've been fine with this graphically. On the midterm, the scores were really high graphically, but then we kind of struggled once we started to do this analytically. So we're looking at a couple problems there. Okay, the limits analytically was, again, one of our lowest sessions, so I'm going to really quickly run through all of the limits rules. We'll look at a couple problems. So if you've got absolute values, blow this up a bit. So what we'll do with those absolute values is we'll plug in to see what happens to the point after that absolute value makes it positive, to check and see if the limit is still the same from both the left and the right. If the limits from the left and the right are not the same, so in this case our limits are not the same here, then our general limit cannot exist. Okay, so for this one, if I plug in -7 minus a little bit, that's like -7.1, then I'll have a negative number when you add 7. Under the absolute value, that would become positive on top, but on bottom it would stay negative. So I've got a positive divided by a negative is a negative. For this bottom one, -7 plus a little bit is like -6.99999. If I add 7, that's still a positive number, so I've got a positive divided by a positive is positive. So if you're just looking for a one-sided limit, we can find them. But if you're looking for a general limit, then it doesn't exist for this one. Any questions on the absolute values? Okay. Then for composite functions. Okay, welcome back. So then for composite functions, no, you're okay. There might be some intermittent stuff on my end. Now we've got, I believe, if I remember right, one of you is out of the country, so I'm running a VPN right now. If it keeps crashing, I can always turn it off. We'll see if that's better. Okay, so for the second one, limits to composite functions, what we're doing is we're plugging one function into another function. So I'm not multiplying here. I'm taking the limit of f of g. So for this one, if g of x is 1 over x, then I've really got the cosine of 1 over x for my total function. Then we can look at our inside part first, just the 1 over x, to take our limit as we approach infinity, which is 0. And then the cosine at 0 would be 1. Therefore, my composite function is 1. So anytime you've got a composite function, a function inside another function, you always need to start with the inside part and then work your way out. Okay, limits by factoring, just factor and cancel. Here's x plus 1 and x plus 1, so I'm left with 1 over x minus 3. Be careful, I can't remember who, but I know on one of the midterms that I saw, someone canceled and then just kept this as x minus 3 over 1. I can't flip the fraction like that, so anytime you cancel, there's an understood 1 if you cancel everything from one side. Okay, then floor functions. So the symbol for this looks kind of similar to an absolute value, but we've got that extra mark on the bottom. Just means we're going to round down to the nearest integer. So if I had 6.1 and I took the floor function, I would end up with 6. If I had 6.9, I would still end up with 6. negative 0.1 would end up at negative 1. Okay, so floor just rounds down to the nearest integer. You could also have a ceiling function that does the opposite. So that would round up to the nearest integer. 6.9 would round up to 7. 6.1 would still round up to 7. Negative 0.1 would have a ceiling of 0. Okay, floor functions round down to the nearest integer. So for this one, if I plug in negative 2 plus a little bit, again, that's like negative 1.99999 times 2. I'm going to end up with a number that is a little bit bigger than negative 4. So that's like negative 3.99 plus 1. Will give me a number that is a little bit bigger than negative 3, or like negative 2.999999. If I round down from that, I'll get to negative 3. Any questions on floor functions? Okay. Limits by rationalization. My cue here is anytime you see a root. So for limits by rationalization, what we're going to do is we're going to multiply by the same two terms, so the same binomial, but with a different sign. And what that does is that creates a perfect square. Hopefully that perfect square will cancel with what was on top, or with the part of our fraction that did not have a root. And that'll allow us to simplify and plug in. So for this one, I'm going to multiply by the same binomial that had the root with a different sign. If I do, this root x plus 7 times this root x plus 7 will be x plus 7. Root x plus 7 times 3 will cancel out with the negative 3 times root x plus 7. So those two terms both go away, and then negative 3 times 3 is negative 9. Okay, so that gives me x plus 7 minus 9 is x minus 2, which can cancel with my x minus 2 on top. Now I can plug in 2, because I won't be dividing by 0. So that gives me root 9 plus 3, which is 3 plus 3, or 6. For piecewise functions, piecewise functions we'll be working with a lot for your AP exam, because we can look at differentiability and continuity with them as well. So for the limited piecewise functions, at any breakpoint, you'll need to check the limit from the left and the right to see if there is a general limit. So for this one, if I wanted to know, is there a general limit at x equals 1? I would need to test from the left, which means I would be testing with this top function, since to the left of 1 would be less than 1. If I plug in negative 1, actually made a mistake here. This says positive 1, this says negative 1. Okay, I'm going to set my breakpoint at negative 1 then. My bad. Okay, so if my breakpoint's at negative 1, if I plug in negative 1 minus a little bit, this will be using my top function. So this will be negative 2 minus 6 is negative 8. If I do the same thing down here, that would be a negative 1, or positive 1/2 minus 1 is negative 1/2. Those are not the same limits from the left and the right. Negative 8 is not the same as negative 1/2. Therefore, our limit does not exist. Okay, any questions on limits of piecewise functions? Okay, if you do want to test for differentiability, then you need to test for having a general limit and being continuous beforehand. So you must have a general limit in order to be continuous, and you must be continuous to be differentiable. That means if I tell you a function is differentiable, you already know that it is continuous and has a general limit. But if I tell you a function is continuous, that doesn't tell you anything about differentiability. However, you do know that it has a general limit. So it only works one way. I must have a limit if I am continuous. I must be continuous if I am differentiable. Okay. Al-Hospital's rule says as long as we take a limit and we get either 0 over 0 or plus or minus infinity over infinity, then we can derive the top and bottom separately and take the limit again. I believe everyone got that right on the midterm, so I'm going to kind of skip over the next couple of these. Squeeze theorem, you're going to see this graphically on the AP exam more than you see this analytically for the multiple choice. However, on your free response, you can cite squeeze theorem as the reason why you did something in a proof. So you do need to remember the name of the theorem. But squeeze theorem tells us as long as we know that a function is always between two other functions, then the limit of the top function and the bottom function should also be the limit of the middle function at that point. Okay, and the last one, limits at vertical asymptotes. So vertical asymptotes are any time when we're dividing by 0 and we cannot cancel. If we could cancel, we would have a removable discontinuity instead. So if you can cancel graphically, you'll end up with something like a hole. If you cannot cancel, you'll end up with something like this. So a vertical line that our function can never cross, which we call a vertical asymptote. So if you have a vertical asymptote, we would need to test the one-sided limits to see whether we're going to infinity or negative infinity around those points. If they're both infinity, we can say that we have a general limit of infinity. If they're both negative infinity, we can say we have a general limit of negative infinity. But if they're different, then the limit does not exist. The general limit does not exist. So for this one, if I try to plug in 3 or negative 3 right now, I'll be dividing by 0, which I can't do. That's undefined. So if I take the limit as we approach negative 3 from the left, so that's like negative 3.000001. When I square that, I'll end up with a number that is slightly bigger than 9. So on bottom, I'll have 0 plus a little bit. On top, I have this negative 2. So that's a negative divided by a positive gives me negative infinity. Okay, if I go from the right instead, then when I square this, I'll have a number slightly less than 9. So on bottom, I'll have a negative number. A negative divided by a negative is a positive. Because negative infinity and positive infinity are not the same, my general limit does not exist. Okay, that's it for limits going to one number. I also need to look at limits at infinity. So I'll do that really quickly. Our general rule for limit at infinity is based on growth rates. So if you are growing faster on the top of your fraction, you'll end up pulling towards infinity or negative infinity. If you're growing faster on bottom, you'll pull to 0. And if you're growing at the same rate, you'll pull towards the fraction of your coefficients. We can also talk about your horizontal asymptotes, which are your limits at infinity or negative infinity, with their whenever your largest power is on top or your growth rate is faster on top. You will not have any horizontal asymptotes. Your horizontal asymptote will always be 0 if you're going faster on bottom, and the fraction of your coefficients if you end up growing at the same rate. It is possible to have two different horizontal asymptotes, one for positive infinity and one for negative infinity. And to find them, you can just take the limits at infinity or negative infinity. So horizontal asymptotes are lines that our function approaches as we get to infinity. It is possible to cross a horizontal asymptote, but it is not possible to cross a vertical asymptote. Okay, if we are not dealing with polynomials, then we have a growth rate chart that we can use. So factorials grow faster than exponentials. Exponentials grow faster than polynomials. Polynomials grow faster than logarithms. Logarithms grow faster than sine or cosine functions. And sine or cosine functions grow faster than constants. Our pre-calc class came up with feed elephants peanuts, love someone cool. Factorial, exponential, polynomial, logarithm, sine or cosine, constant. Okay, so to throw a couple examples on here. Because factorials grow faster than exponentials, my fastest growth rate is on top. Since these are both positive, I'll go to positive infinities. That means we have no horizontal asymptote. Exponentials grow faster than polynomials. Therefore, my fastest growth rate for this one is on bottom, and I'll approach 0. For this one, I can actually use property of logarithms to pull this down to see what my fraction of my coefficient is, but this ln x on both sides is my fastest growth rate. So my fraction of my coefficients is actually 7 over 5, because logarithms grow faster than constants. Okay, any questions on any of those three examples? Okay, then that's it for the lesson. I'm going to wrap things up with a couple sample problems, and we'll see how we do. Oh, sorry, one more thing, I forgot. Infinite Riemann sums. So Riemann sums are a way that we can estimate the area underneath a curve. You guys have been able to get the area underneath the curve using an integral. So the integral of f of x in terms of x from a to b would tell us the area underneath the curve from a to b. So let's say here is a, here is b, and you're getting all the area in between, right? Okay, so what we're really doing there is we're stacking up a bunch of infinitely small boxes, so infinitely many bases with infinitely many bases and heights, where all of your bases are infinitely small. Okay, so if I wanted to write that, I could say we are summing up a number of rectangles from rectangle 1 to rectangle infinity that have some height and some width. Or if you want to think of it this way, I'm taking whatever my y value is right now and I'm multiplying by my change in x. That's my f of x times my change in x. For every possible rectangle that I can make from rectangle 1 to rectangle infinity. Okay, so we could say I'm summing up all of the bases times the heights, where my function of x, my height, is going to start at plugging in a into my function. So my first height would be f of a. My second height would be f of a plus 1 dx, one infinitely small movement to the right. My second one would be 2 infinitely small movements to the right, right? So if I keep doing one more movement to the right to get my next heights, then we can call that an iteration, which we can subscript as I. So that iteration is going to start at 1, and it'll just increase by 1 every time. 1, 2, 3, 4, 5. For every possible rectangle that we have. And this summation will just add up all of those bases times heights. So I'll end up getting all of the areas of these rectangles summed together. Okay, once you've got those heights, in order to get the area, I also need to multiply by my change in x. To figure out how much your change in x would be, I could take your end point and subtract your start point, so that's b minus a, and then divide by n, where n is the number of rectangles. Okay, so that means my function ends up looking like this. So I'm taking my height at my start point plus however much we have gone over, which is my change in x, or b minus a over n, so just substitute that in, times I. So that's how many times we've moved over so far. Okay, once I've got my height, I can multiply by the base of that rectangle, which is an infinitely small change in x. Okay, if I want an infinite number of rectangles between a and b, so that would give me the perfect area between a and b. If I have infinite rectangles, then I'm really just drawing lines. If you're drawing infinitely many lines between a and b, you should get the exact area. Then I could take this sum and make it a limit. So the limit as n approaches infinity of this sum will end up giving me the perfect area underneath the curve. So this is the limit definition of an integral. Okay, any questions on what we did? All right, cool. So now we're done. And I'll jump into a couple of our practice problems here. Okay, I wasn't planning on starting with this one, but since we just did this, let me jump in then. There we go. Okay, I want to know which of the following limits would be equal to the integral from 3 to 5 of x to the 4th power. Okay, so I'm going to have you guys help me out. In order to match this, I'm going to look at our change in x first, because it looks like that part is different. And then we'll look at what our function should be. So what's our formula for our change in x? Okay, b minus a over n. So for us, what should our change in x be for this problem? Okay, 5 minus 3 over n, or 2 over n. Okay, so already I can eliminate a and c. So if you're really short on time, you can make this a 50-50 just by looking at your change in x. Okay, then I'm going to look at the next part. Should be my function of a plus dx times I. What is my function right now? X to the 4th power. So that means f of a plus I dx is the same thing as a plus I dx to the 4th power. Junho, what is a? Okay, a is 3, so this is 3 plus, Oliver, what's dx? That's that's f prime x, I think. We've already solved for dx in our first step. I just need to copy this over. So what's our dx? 2 over n. So this will be 2I over n then. Okay, so the way that we've written our formula on the other page, this would be the limit as n approaches infinity of the sum from I equals 1 to infinity of 4th power 3 plus 2I over n to the 4th power times 2 over n. Okay, so which of these matches? D. Okay, so just using a different letter for their variable, but it's the same formula that we had on the last page. Any questions on this one? Nope. Okay. I'm going to zoom back up and we'll try a couple more of these. So there is a release test from 1988 that I'm allowed to talk about. So I've pulled all of the limits questions from 1988 and we'll go through those really quick. And if we've got time, we'll keep going with another set. Okay, so I've got the derivative is cosine derivative of f is cosine, derivative of g is 1 for all x's, and f of x and g of x at 0 is 0. So what should the limit as x approaches 0 of this function be? Okay, so if I just take the limit as x approaches 0, what happens if I just plug in 0 right now? Yes. So right now, if I plug in 0, I would get f of 0 over g of 0. So what is my limit as x approaches 0 if I just try to plug it in? Okay, 0 over 0 over 0. Okay, so because this is 0 over 0, what do I have to do? L'Hospital's rule. Okay, so this limit should also be equal to the limit as x approaches 0 of what? Okay, you're both right. F prime x is the derivative of f over derivative of g. Perfect. Or we were given that, so that's the cosine of x over 1. What's the cosine at 0? One. So this is 1 over 1, or b. Okay. I think I'm going to alternate, so that might be faster. So Junho, I'm going to start with you on this one. Ah, sorry. I need to disable that on-screen keyboard next time. Okay, so Junho, back over to you. At x equals 3, I want to know, is this function continuous, and is this function differentiable? So what do I have to test first? Okay, general limit. So I'm going to plug in 3 from both sides. What happens if I plug in 3 from both sides? Nine and... Okay, not 9 and 0. Okay, so I've got 9 and 9. I'm just going to write this as a general limit. So the general limit was 9. And if I plug in 3, I'm also using the bottom function, so that's also 9. Okay, what else do I need to test? Okay, derivative from the left and the right. So we've already proven it does have a general limit, and it is continuous. So to prove differentiability, what happens when you derive the top? Okay, and the bottom? 6, when x is greater than or equal to 3. Okay, so is this function differentiable at x equals 3? Yes, because the top is 6 and the bottom is 6. So which answer is correct? E. This one is both continuous and differentiable. Perfect. Okay. Oliver, over to you. So what will this limit end up being? So we're on number 29 from the worksheet. Okay, this limit's in a special form. Do you know what form this is in? Okay, so this is actually the formal definition of a derivative. If h is my change in x. So knowing that, what's our function then? Perfect. And since this limit is the derivative, my answer should be the derivative. So what's the derivative of tan 3x? Perfect. And that's it. Okay, Junho, over to you. Okay. I want to know which of the following should be true. If I have a general limit of my function, if my general limit of the function is 7, do I have to be continuous? No. Okay, so this one does not have to be true. Do I have to be differentiable? No. When I plug in 3, do I have to get 7? So all we know is that our general limit is 3, so the counterexample would be something like this. So here's a point that's undefined. Kind of drawn this on the wrong side, haven't I? So x approaches 3. Okay. My point at 3 is undefined, but we're approaching 7 from both the left and the right. Okay, so this one does not have to be true either. So this one's actually none. Okay. Oliver, over to you. I'm looking for which of these equations would have y equals 1 as an asymptote. Now, if I have y equals something as an asymptote, y equals something would be a horizontal line. So I'm looking for which of these equations has a horizontal asymptote at y equals 1. Horizontal asymptotes are limits as you approach infinity or negative infinity. So which one of these has a limit as you approach infinity of 1? Okay, so e as I approach infinity would be e to the negative infinity, which is 1 over e to the infinity, which will approach 0. So not e. D, if I approach infinity, my power is biggest on top, so I should approach positive or negative infinity, so this will keep going up forever. Okay, Oliver, I'm going to jump to you. Can you help us out? I'm sorry, Junho. Can you help us out? C, right. So if I'm approaching infinity and my powers are the same, I'm going to approach the fraction of my coefficients, which in this case is 1 over 1. So that gives me y equals 1 as my horizontal asymptote. The key here is horizontal asymptotes are limits as x approaches plus or minus infinity of your function. Okay, this one's a little bit more involved. So I think we'll tag team it, and I'll just do step by step and bounce between you. And we'll probably stop here because we've been going for quite a while now. So I have this differentiable function with all of these properties. My derivative at 1 is 6. My second derivative at 1 is 18. My derivative at derivative at any point is ax squared plus bx. And our integral from 1 to 2 of f of x is 18. I want to figure out what f of x is. Okay, so we need to solve for a and b first. Since I already have an equation for the first derivative, and we know what our first derivative is equal to, I can set those two equal to each other. So I'm going to start there. 6 equals ax squared plus bx. Okay, then my derivative at 1 should be 18. So what would my derivative of ax squared plus bx be? Two ax plus b. Perfect. 2ax plus b should equal 18 because the second derivative is 18 as long as x is 1. I can also go back and replace all of these x's with 1 because I have to plug in 1 for that to be true, right? Okay, so this will be 1, 1, and 1. Okay, so that gives me 6 is equal to a plus b, and 18 is equal to 2a plus b. Okay, so now I've got a system of equations. We can solve for a and b. Oliver, if I subtract this bottom equation from the top, what will I be left with? Negative a. Okay, therefore a is equal to 12. If a is equal to 12, then I can take that and plug that back into my first equation. So 6 equals a plus b to solve for b. So 6 equals 12 plus b, or b is minus 6. Okay, so I solved for a and b so far. But I'm not done, because our question asked us to find f of x. So I'm going to go back in and plug in a and b, and we'll see what happens if I integrate this f prime x to get an f of x. And then we'll integrate that one more time to get our 18 and see if we can solve for our function. So if I have f prime x is ax squared plus bx, where we now know a is 12 and b is minus 6. What will happen if I integrate? Okay, 12x cubed over 3 is the same thing as 4x cubed. Cool, minus 3x squared plus c. Okay, so I've got that extra constant c because we have no way of knowing working backwards if there was a constant there, since if we derive a constant, it would be 0. Okay, so now that I know f of x, if I integrate f of x from 1 to 2, I should get 18. So if I integrate 4x cubed minus 3x squared plus c from 1 to 2, we should get 18. Okay, so since Oliver integrated the last one, Junho, what happens if I integrate this? Yep. Okay, you're right, 4. Okay, so my 4's will cancel. So I've got x to the 4th. Okay, again, my 3's cancel. So I've got x to the 4th minus x cubed. Cx, perfect. Okay, and then we integrated from 1 to 2. Okay, so then 18 should be equal to, Oliver, if I plug this in, what's going to happen? Yep, 2c. Okay, minus my lower bound. Okay, so my 1 minus 1 will cancel, so I have minus c here. 2c minus c is c. 16 minus 8 is 8. So I've got 8 plus c equals 18, or c equals 10. Okay, now that we know c is 10, we can go back and plug c into our f of x to get our final answer. F of x is equal to 4x cubed minus 3x squared plus 10. All right, any questions on what we did there? Okay. Well, thank you guys so much for coming. We're right about at the 45-minute mark. On course sites, under online assignments, you should see a day 1 limits assignment. That will be due at 9 a.m. on Wednesday. And then we'll keep going with more limit stuff again at 10:38 in the morning on Wednesday. So same schedule as today. Let me know if you guys have questions on WeChat too. Right. On course sites, you have your assignment under online classes, day 1 limits. It's due at 9 a.m. on Wednesday. Okay, and that'll be the grade for this class. Due by 9 a.m. on Wednesday. So you guys have 46 hours. And then at 10:30 on Wednesday, we'll do our next live session. And we'll keep going with limits. All right, thank you guys so much. I will post the recording as soon as I finish uploading it.